I'd like you to think first about how you can find the derivative of dy dx, okay? Keep in mind that these are parametric curves, right? X is the same as r cosine theta, and y is the same as r sine theta. So I'm defining x parametrically by using the parameters r and theta. And I'm defining y parametrically by using the values of r and theta, okay? And so what I'd like you to do is get together in your breakout rooms for a minute and keep in mind that if we want to find dy dx, then doesn't that mean that we just want to find the derivative of y with respect to, well, t over the derivative of x with respect to t? Well, now, if we think of theta as being the independent variable, right? Theta is the independent variable, then we're going to think of theta as changing. So if I want to find dy dx, then we're simply going to be taking dy d theta and dividing by dx d theta. Using these as my parametric set of equations, if x is defined as r cosine theta and y is defined as r sine theta, we want to take the derivative of y with respect to theta over the derivative of x with respect to theta. On the notes here, I've gone ahead and included my lecture notes just on polar and parametric, or I'm sorry, polar graphs and curves as well, just kind of what the recap would be. So if you have some issues, I would encourage you to go back through the first few slides in this particular component here. One thing I wanted to mention as well is what a negative radius would mean. So sometimes you'll plug in an angle and you'll get a negative r. So let's say, for instance, that I wanted to plot the point 5 pi over 4. Well, that would mean point in the direction of 5 pi over 4 and walk out 1, 2, 3, 4, 5 circles, okay? But if you were to do the point -5 pi over 4, that would mean point in the direction of pi over 4 and now walk backwards 5 units. So that would mean if I'm pointing in the direction of pi over 4, but I walk backwards 5 units, I'm actually moving in the direction of 5 pi over 4. So that's why these are actually the exact same point, okay? That's why 5 pi over 4, right here, 5 and 5 pi over 4 is exactly the same as pointing in the direction of pi over 4 and walking backwards. Okay, so those are exactly the same values. And in fact, there's an infinite number of ways to plot any particular point in polar curves. And we talked about the how to graph a function, but we could also convert from rectangular to polar as well. So practice that. So recognize that cosine theta is x over r, and r is just the square root of x squared plus y squared from the Pythagorean theorem. And if I now manipulate this a bit, then it turns out to be this circle, x minus 1 quantity squared plus y squared equals 1. But not all polar curves have nice rectangular forms, which is the purpose for using polar curves or polar form, okay? But what you should have gotten in your groups here is this, okay? So when you differentiate with respect to theta, you should have recognized, first of all, that this was a product, and this was also a product. And so if I'm differentiating with respect to theta, you've still got to treat r as a variable, because it varies. And so if I was to differentiate, I would differentiate to get the first times the derivative of the second, which is r times cosine theta, plus the second, which is sine theta, times the derivative of r. But notice the derivative of r with respect to theta is dr d theta. And that takes care of the numerator. Well, if you take the derivative of x in the exact same way, okay, then you start with the first r times the derivative of cosine theta, which is negative sine theta. And then you go to the second, which is cosine theta, times the derivative of r, which is dr d theta. And that's why this is our answer. Now we typically just more, importantly, we end up writing it in this form right here, simply because then it becomes something plus and then something minus. One thing that I do to remember this and memorize this is that I recognize that this quantity up top is X, and this quantity on the bottom is actually Y. So if I was to try not to look at this and just come up with that on myself, I would remember that dy dx has an X on top, has X on top and Y on bottom. So we get R cosine theta on top, and we get R sine theta on the bottom. But then I'd remember that top and bottom both have a dr d theta term as well. And each of those are multiplied by the opposite of that function. So if that's cosine theta, then I know that I'm going to be multiplying dr d theta by sine theta. And if this is R sine theta, then I know that I'm going to be multiplying this by cosine theta. And then I just remember the plus is on top, minus is on the bottom. Okay, so if you can try to do the idea here is to try to come up with a way to remember how to find the derivative without having to derive it every time, because that's a pain in the butt. So instead, we're going to go ahead and try to remember this process of constructing it. So that's what I remember anyway. Now, what's cool about this too is, what if we're trying to look for tangents at the pole? So we could look at tangent lines at different R values, at any R value we want, any theta value we want. But if we want to look at the tangent lines at the pole, it actually turns out to be a very simple formula. dy dx at the pole is tangent of that angle. Can anybody think about why that would be true? Why is it that all I have to do to find the tangent lines at the origin or at the pole, I just have to compute what the tangent of the angle is?
Is it because dy d theta is just a change in y, while dx d theta is a change in x, and y over x is tangent?
Well, that's a very good observation, that dy dx is the change in y divided by the change in x. So you would think, well, y over x is tangent, so the change in y over the change in x would be tangent. But it's a little bit, it's kind of like that, except for the fact that it's really just saying if r is equal to 0, then wouldn't that mean that this r is 0 and this r is 0, which would cancel out this entire term and this entire term? So all that's left would be this. But if they have a dr d theta in top and bottom, then cancel that out and cancel that out. And what's left? Sine theta over cosine theta, which is tangent theta. So this is
so close.
It's a shortcut here. And it's really cool because what I think it was Abby that said that, right? What Abby was saying is that it's kind of interesting because isn't the form for dy or for tangent theta y over x? And we're just seeing the tangent of theta is actually the change in y over the change in x as well. It's pretty cool relationship. So what I would like you to do then is remember that equation that we just did back here. Okay, r equals 1 plus sine theta. What I'd like you to do is find the slope of the tangent line at pi over 3. So why don't you find the slope of the tangent line at pi over 3? Okay, which really just means find this slope right here. Let me ask you this then. Let me ask you an easier question from Calc 1. How do I find dy dx? What do I need to be given? How do I find dy dx?
You need a y value and some sort of x value.
And then I take the derivative of that with respect to x. Isn't that what that means?
Oh,
So
I just found it.
Function y, and then I differentiate it with respect to x.
So then could we differentiate the original equation that we got of r equals 1 plus sine theta? Differentiate both sides, and that gives us dr d theta, dr over d theta equals cosine theta.
That's right. Because
Like
all we got to recognize is that d theta of r means to take the derivative of your function. It's just that now your function is r in terms of theta. So notice that when I try to take my derivative, all I'm doing here is recognizing that if r is 1 plus sine theta, then I differentiate r, which is cosine theta. So now I can plug everything into the appropriate spot, and I get dr d theta here and here. I get r here and here. I plug everything in and simplify, and I get this is the formula to find my slope. So if I'm given a polar curve and I want to find the slope of this particular polar curve, this is it. So that must mean that dy dx at pi over 3 just means to replace all of these values with pi over 3 and simplify. So because I ended up getting all of these complex fractions, I just chose to multiply top and bottom by 2. And what was nice about that was when we did so, we got 1 plus root 3 on top, negative 1 minus root 3 on the bottom. Turns out those are the same, just off by a negative. The slope at pi over 3 is negative 1. Let's just revisit that on the graph. If we just found out that at pi over 3, the slope is negative 1, that means that by the time I'm at pi over 3, I better see a negative slope, which sure enough I do. And it's a slope of negative 1. Down 1, right 1, down 1, right 1, down 1, right 1. And so this formula now for finding tangent lines is literally just the process of finding what the slope is at each individual location. So while we're at it, why don't we go ahead and find the slope at, why don't we go ahead and find the slope? You could just do this individually. I'd like you to find the slope at the pole. Okay, so go ahead and think about how to find the slope at the pole. So what are some thoughts about how you could find dy dx at the pole?
The tangent of pi over 3.
Okay, so notice that you're saying let's just find tangent at pi over 3. Okay, because if I want to find the tangent of the pole is when the radius is 0, right? That's at the pole. So why did you pick pi over 3? I'll tell you why it's not pi over 3. Let's go back to our graph. Pi over 3 is not where the pole is because this is the point at pi over 3. That is not the point at the pole.
So then should it be 3 pi over 2?
Isn't that where the radius is 0? We did that work earlier. We saw that the pole occurred at 3 pi over 2. But let's say that we didn't have the graph and we were just doing this by hand. How would I do that? Well, I'd have to first of all start off by figuring out what angle gives me 0 for r. In other words, when is negative 1 equal to sine theta? When is sine theta negative 1? At 3 pi over 2. So it's actually not tangent of pi over 3, it's tangent of 3 pi over 2. Okay. What is tangent of 3 pi over 2?
Oh, well, it's on the unit circle 1 over 0.
Yeah, it's 1 over 0. Oh, crap. Wait, that's undefined.
So my first thought when you asked us to find that slope was that it was a cusp. Am I right?
That's exactly right, because if I'm saying find the slope at that point, and the slope is a cusp, and the point is a cusp, we should realize automatically that it can't have a slope because it's got two different slopes, and therefore it's not differentiable. So we should be able to see graphically that it wasn't differentiable, but then if we actually go back to the reasoning, the reason is because tangent of 3 pi over 2 is undefined. Make sense?
So I have a question in terms of well, when we were trying to more like condense what dy dx is, and it said, oh, we have cosine theta times cosine theta. Why is that cosine 2 theta instead of cosine theta squared?
That is a great question. Let me explain why. It's cosine squared theta minus sine theta minus sine squared theta. If I were to expand it out, right?
Mm-hmm.
Cosine squared theta minus sine squared theta is cosine of 2 theta.
Oh, okay.
It was just an identity. I'm sorry, I jumped the gun on that one. So if you didn't notice that, then you could obviously just leave it in the other form, I suppose. But I like to try to simplify quantities whenever possible. And so that's what we did. So in the top, I ended up factoring out a cosine theta and just got 1 plus 2 sine theta. But in the bottom, I didn't want those 3 terms, especially because I noticed that cosine squared minus sine squared is cosine 2 theta. All right. Cool. Well, that takes care of derivatives. But I'd like to go back to Desmos real quick. And let's say that I wanted to do a problem like this. Okay. Let's say I gave you r equals cosine of 2 theta. If you graph this, whenever you've got a double angle, sine or cosine of a double or triple or quadruple angle, turns out to form this little rose pattern with petals. Okay. And let's say that I wanted to find the area of just one of these petals. Well, because this is a polar equation, I got to obviously integrate somehow, but is it really just going to be the integral of r? I mean, if I take the area under a curve, then we derived the fact that by coming up with the individual areas of the rectangles, which were just height times width, or y times dx, that's why we were integrating the f of x dx. But there's got to be a way to still integrate involving polar curves so that we can still find areas. So before we continue, let's go ahead and take a look at, so keep that graph in mind for a minute. And let's head back to here. All right. So if we want to now do area in terms of polar coordinates, okay, then this all leads back to finding areas of sectors, okay? So the way that we start this off is just realize that the area of a circle is pi times the radius squared, right? Pi times the radius squared. If I wanted to find the area of a semicircle, then I just take the area of the circle and cut it in half. If I wanted the area of a quarter circle, I would take the area of a circle and cut it in fourths. But what I'd like you to recognize here is that every one of these has an r squared. But let's focus on the coefficient. The coefficient is pi here, pi over 2 here, pi over 4 here. So if we think about the angle that we turned through in order to create a full circle, we turned through an angle of 2 pi for the full circle, but I multiplied over here by pi. For a half circle, we turned through an angle of pi, yet we multiplied by pi over 2. For a quarter circle, we turned through an angle of pi over 2, but we multiplied by pi over 4. You should realize here that this is really just half of whatever angle is that we turned through. So that's why in general, what we should notice here is that the area, over here of some sector of a circle is going to be r squared, obviously, times half of the angle that we turn through. So this is the area of any sector of a circle. So when I say a sector, that just means if I have this piece here and I have this piece here, that's just a sector of the circle. Let's curve that so you recognize that it is not a triangle. Okay, so this is just going to be the angle that I turn through, and therefore this piece right out here is referred to as our arc length, S. Okay, and so if I want to find out the area of this sector, I just simply take half of, or I square the radius and take half of theta. Okay, well, what does that mean? It means that if I want to create the formula, okay, for area of some piece, let's say that I want to shade this yellow piece right over here, and I call this function r equals f of theta, like r equals 1 plus sine theta, for instance. Well, I'm obviously going to be turning through a certain angle. So let's just say that I'm turning through from theta equals A to theta equals B. So I'm first of all going to be integrating from A to B. But because these are theta values, I know that I'm going to be integrating with respect to theta. So I could see that if this right here is a theta value, and that's a theta value, then I better be integrating d theta. Well, that takes care of the fact that that's my change in the angle. So all that's left is to integrate 1/2 r squared. But r is the function. So all I'm doing is taking the area to be 1/2 the integral from theta A equals to theta B of the function squared d theta. Everybody cool with that? All right. Well, let's go ahead and work on that then. So let's just say that we went back to Desmos and we wanted to find the area of this piece, I'm sorry, of this whole piece right here, of just one petal. Okay. Well, first of all, we'd have to recognize that this is my function. So the first thing I know I'm going to do is I'm going to integrate this function squared. But what's most important is I have to figure out where does it begin and where does it end. So I need to figure out what is the pole, because it looks like I'm going to be turning. I'm going to try to follow this as easily as I can here. So watch the starting point here. Let's just, I don't know if it's going to start at an angle. Well, let's see. What is cosine of 0?
1.
Cosine of 0 is 1. So what that means is that the angle of 0, I'm going to start out here at 1. And as I start rotating through, I'm going to follow what happens as I continue to move through this piece. It's going to come to the pole and continue my curvature all the way down and around. It's going to come back to the pole and continue the curvature. It's going to come back to the pole, continue the curvature. Come back to the pole, continue the curvature until it reaches back to the beginning. So that's basically what would happen if I were to graph this by hand, okay? So let's go ahead and look at what that would look like if I were to set this up. If I wanted to find the area enclosed by one loop of the 4-leaf rose, then the first thing I got to do is I've got to write 1/2 times the function squared d theta. But I got to figure out where this hits the pole, okay? And so that's why I've got to make sure that r is equal to 0, okay? So let's find out on the side over here, where is r equal to 0? Because that's the pole. So we're just saying, when is cosine of 2 theta equal to 0? All right, well, where is cosine equal to 0? Where would
Pi over 2.
pi over 2,
and 3 pi over 2.
and 3 pi over 2. Right? But notice that what I've done is I've solved for this angle. So that's why I know that 2 theta is equal to pi over 2 and 3 pi over 2. Which means in a second I'm going to have to divide by 2 in order to find what the actual angle is. But secondly, because I see that there's a coefficient of 2, I need to list out 2 rotations. So that by the time I divide by 2, I get all of the values from the first rotation. So if I now divide by 2, I get that my values for theta are going to be pi over 4. Then I'm going to hit the pole again at 3 pi over 4. Then I'll hit the pole again at 5 pi over 4. Then I'll hit the pole again at 7 pi over 4. And so now I just need to think about my graph. Okay, well that's why Desmos can help here, because if I know that I'm going to be starting, let's say that I start over here, okay, and I go from 0 to pi over 4, that's not going to be one pedal. So maybe you're like, well, maybe I got to go until I get to another pi over 4. So that would mean that I'd have to go from pi over 4 to 3 pi over 4 again. So I could go from pi over 4 to 3 pi over 4, because that would give me this pedal. Or if I don't do that, I could just say, if this right here takes me to pi over 4, then wouldn't that mean this back here would take me to negative pi over 4? And so if I go from negative pi over 4 to pi over 4, I still get the same pedal. So this is why it's helpful and important for us to be able to, at this point, to at least understand what the graph is going to look like, or have an idea about where things are located on this graph, because what we're going to do on this problem, close that, there we go. What we're going to do on this problem is integrate from negative pi over 4 to pi over 4. So that's going to give the right pedal. If you went from pi over 4 to 3 pi over 4, you'd get the same answer. So this is just a matter of integrating this function. We first of all have to do a power reducing formula here, which would be 1 plus cosine 4 theta over 2. And so if I pull out that extra 1/2, I get a 1/4 out here. And now I'm integrating d theta, and then I integrate cosine of 4 theta. And that's where I can get the derivative of 4 theta, which is 4, multiplied by an extra 1/4, blah, 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 get your answer. Okay, I mean, this is just a matter of integrating. The tough part is setting up the integral, okay? Everybody cool with that?
I have a question. Because that's just for one pedal, right?
That's just for one pedal. So if we wanted to find the total enclosed area of this curve, we would just multiply pi over 8 times 4 to get pi over 2, which is kind of cool, because it turns out that the area is actually just pi over 2. The total enclosed area is pi over 2. That's pretty darn cool. Cool with that?
Talking about the enclosed area of the pedal?
Just one pedal would be pi over 8. We just calculated that. But if I wanted to find the area of this pedal plus this pedal plus this pedal plus this pedal, it's just 4 of one pedal. So if one pedal from negative pi over 4 to pi over 4 was pi over 8, then all we had to do here is find the area enclosed by one loop of the 4-leafed rose, or one pedal. Okay.
Okay.
Cool. All right, well, the last thing we're going to go over here is finding the area between curves. And so the area between curves is actually kind of cool too, because it turns out to be very similar to what we did before. If I wanted to find this yellow area between curves, between two angles, from angle A to angle B, then just keep in mind all we're doing, the same exact thing that we did before, is that we're finding the total enclosed area inside of the red curve, and then we're taking away just all of the area inside of the green curve. So it turns out to be that similar idea in terms of how to find area between curves like we did before, only now it's going to be the area of the outside minus the area of the inside. But since they both have the same coefficient and limits, we could actually just combine it into one. So we've just got to figure out where's the outside function, where's the inside curve, and then subtract the two. Okay. So the ones we're going to deal with is right here. Okay. Same thing as r equals 1 plus sine theta. And we're going to do this by hand. Okay. So even though it's on the notes here, I'm going to do it down here. Okay. Okay, so we want to find the area enclosed by r equals 3 cosine theta and r equals 1 plus sine theta. Okay, or 3 sine theta, not cosine theta. Okay, well, I just want to talk, we already saw what this graph looks like. Okay, I'm going to show you another way to just kind of sometimes think about what a graph looks like. You could actually convert this into polar form or a rectangular form. So let's go ahead and do that. So we know that r is equal to 3 times y over r. Okay. But if I multiply both sides by r, I get r squared equals 3y. But r squared is just x squared plus y squared equals 3y. And I could continue to go through this process to continue to solve, but it turns out at this point I already know what it is. It's a circle. Okay. And when I look at this circle on Desmos, this circle is going to, because it's in terms of sine theta, anything in terms of sine theta will always be symmetric to the y-axis. Anything purely in terms of cosine theta will be symmetric to the x-axis. So r equals 3 sine theta is actually going to be the circle symmetric to the y-axis with a radius of 3. So notice how this right here is 3. There we go. So we could see that this is going to be a circle with a radius of 3. Now let's go ahead and draw our cardioid. Remember that our cardioid...
Professor, are
Yeah.
you trying to show us Desmos? Because we're still in
sorry.
OneNote.
Sorry about that. Yeah, I am. Sorry, which means you must have missed all of this as well. So, so in this case right here, r was equal to 3 sine theta. I was just showing you how another way to kind of think about what a graph would look like is to convert it into rectangular form. So we convert sine theta into y over r. And then if I multiply both sides by r to get r squared equals 3y, r squared is the same as x squared plus y squared by the Pythagorean theorem. And I could continue this by subtracting 3y and completing the square and so on. But it turns out at this point, since I see x squared plus y squared, I know that this is going to be a circle. So we're just looking at Desmos at this point. And we should realize that 3 sine theta is going to be symmetric to the y-axis, but it'll also have a diameter of 3. So it's going to be touching the origin, the pole, extending out to 3 in the y direction, and that is what r equals 3 sine theta looks like. What if it was r equals 2 sine theta? Now it's the same. R equals sine theta? Now it's the same, just smaller diameter. But what if we were to convert this to cosine? What would happen? Now it's symmetric to the x-axis. Right, so this is what trigonometry taught us. And if it didn't, then review this and get an idea about how to understand polar curves. But we already graphed r equals 1 plus sine theta as well. Okay? And so what we're looking at here is that these have intersected somewhere. And we want to be able to find out the area that lies inside, I guess I can't say enclosed by, so I've got to say in this case, the area inside of this and outside of this. Okay, So in some way or another, we've got to get an idea about which is which, okay? So it's inside of 3 plus sine theta, but outside of this shape. Now let's say that we have no idea what these shapes look like. It can help to graph them, but let's just say blah, 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 there's r equals 3 sine theta, okay? And then this is going to intersect somewhere else, and this is going to be something like this, and that's going to be 1 plus sine theta. If I'm saying inside of 3 plus sine theta, but outside of the orange one, then that would mean that the region I'm referring to is all of this stuff. Right? Because it's inside of the purple, but outside of the orange. So even if you don't know what these graphs look like, you should be able to recognize what that means. And we should be able to recognize that this here is going to be from my formula, my f of theta, or my outside one, while this right here will be my g of theta, which is my inside one. But now let's look at Desmos. If we look at Desmos, what we're looking at here is that we're referring to this piece. Everything inside of the circle, but outside of the cardioid. Okay, so what do you think is going to be necessary in order to do this?
The area of the circle minus the area of the cardioid.
Yeah, but the problem is if I were to just take the whole area of the circle minus the whole area of the cardioid, wouldn't this all here, even all of this stuff down here, be the cardioid?
We would need to figure out, firstly, the area of the cardioid included in the circle.
Okay, so first we would find this area only in the circle, so we'd have to find the area of the cardioid by taking out all of this stuff. Ugh, it's getting even worse. But yeah, you could do that, for sure. Turns out there's a much easier way though, especially if you look back to...
Professor, I might just be tripping here, but could you use something with like the disc or washer method or something along those lines? Or
Well, disc and washer, notice, would be a volume. That would be rotating.
Oh, got it.
We're not dealing with rotation of polar curves, so don't worry about that. But I want to just revisit what we're trying to do. We're trying to find an area. Wasn't this what we needed in order to find an area? So doesn't that mean that we need to know the angle that we're starting at and the angle that we're ending at? And then we just realized that we're taking the outer edge and subtracting the inner edge, which is what we notice right here. So I'm going to go back again. Let's go to Desmos. And what do you think we're going to need to do if I want to find all of this area?
Find our interval line?
Find your what?
Our interval of integration.
Yeah, so I need to know my A and B. So what are A and B representing?
Where they intersect.
So doesn't that mean I need to know where it begins and where it ends?
Pi over 6 to 5 pi
I
over
need
6.
to know this angle right here, which is going to be theta equals A. And I need to realize that I'm going to be integrating all the way through here until I get down to theta equals B. We don't have to do anything about trying to find the area of the cardioid and subtract those extra pieces down below. We've just got to find the area from A to B. And that's it. Okay. So let's go back to here. Let's find that. So if we find that, then all we need to know is where do they intersect? So we need to know where does 3 sine theta equal 1 plus sine theta. So if we subtract sine theta, we get 2 sine theta equals 1. Okay, we know that sine theta is equal to 1/2. We know that sine of theta is 1/2 in the first and second quadrants, so at pi over 6 and at 5 pi over 6. And so if they're going to intersect at those locations, then that must mean that I'm just simply integrating here. from pi over 6 to 5 pi over 6. And now for our formula. It's 1/2 times the outer curve squared, which is 3 sine theta squared, minus the inner curve squared, which is 1 plus sine theta squared d theta. Now maybe you were like, man, but how am I supposed to know what these graphs look like without looking at Desmos? Well, keep in mind, there's another one to know which one is on the outside and which is on the inside. Just pick something in between. Pick something from pi over 6 to 5 pi over 6. Like what?
I just picked pi over 2.
Sure, what's pi over 2? So let's see, what is 3 sine of pi over 2? 3. What is 1 plus sine pi over 2? 2. 3 is bigger than 2. So 3 is further from the pole than 2 is, so that must mean that that's going first. Right, so notice at that point, this is just a matter of integrating, and that would allow us to find our answer. Okay? Everybody cool with that? So if you really want to look at the work here, you can go through that. I won't go through it. But you would expand it, integrate each term, and so on. And sure enough, you get an answer of pi. I love these problems. All of that crazy area, all inside of there, is equal to exactly pi. Crazy. And that's that. You have made it through all the content of Calculus 2. Congratulations.